Morning, afternoon, and evening, everyone. I'm Shenzhen from Wenzhou King University, Wenzhou, China. It's a great honor for me to present my paper at WCV workshop. My paper title is SAPNet, Segmentation Aware Progressing Network for Perceptual Contrasted Learning. Our group consists of 4 members, including our advisor, Dr. Gaurav Gupta. This is a brief outline for today's presentation, including an introduction, the relevant literature, the proposed methods, experimental comparisons, and the conclusion. Let's start with image de-learning, an urban research problem for many decades. We begin with the de-learning comparison and the synthetic learning images on the top row and the real-world learning images on the bottom row. As we can see from this figure, compared with previous state-of-the-art methods, our proposed SAPNet had the best performance in terms of ring removal, edge preservation, blur suppression, and color balance. As we can see from the previous figure, de-learning has several challenges. First, most methods are trained on synthetic images, which lead to poor generalization ability to real-world learning patterns. The semi-supervised and unsupervised learning methods attempt to address the former limitations by transferring the knowledge from the synthetic domain to the real-world domain. However, these methods are very inflexible with diverse learning patterns. The multi-scale methods try to address ring strikes of different scales and magnitudes. However, they are heavily relied upon images resized to different scales. Therefore, the learned neural network has huge parameters and low inference time, which is unsuitable for real-time applications and mobile development. Furthermore, all these 3 state-of-the-art approaches focus on long-level image restoration and ignores the rich high-level semantic details, which is important for high-level vision tasks such as object detection, instrument segmentation, and semantic segmentation. These are the supervised and semi or unsupervised methods mentioned in the previous slides, for example. And these are the strategies for de-learning recommended by recent state-of-the-art papers, including the recurrent network, which maintain an affordable model size, multi-scale fusion, and dialectic illusion strategy to capture dense and heavy ring strikes. The semantic segmentation and contrast learning, on the other hand, help us learn the rich semantic details in the background learning layer. In this paper, we learned from previous state-of-the-art and propose a new model called SAPNet, Segmentation Aware Progressive Network. Our SAPNet joins a de-learning network for supervised ring removal, a segmentation network for unsupervised background segmentation, and the VGG network for perceptual contrast. Let's say we have learning image here. It will first enter the de-learning network. The de-learning network comprises of 6 progressive dilating units which have shared parameters with each other. Each progressive dilating unit have dilated convolutions of different dilation rates to cope with multi-scale ring strikes. After the de-learning process is finished, the de-learning image will join with the ground truth image to calculate the negative SSIM loss. The negative SSIM loss will then be merged to the joined loss. After that, the de-learning image will enter the segmentation network to compute the unsupervised semantic segmentation loss. After that, the ground truth image, the de-learning image, and learning image will join with each other into the VGG network to calculate the perceptual contrast loss and the learned perceptual image similarity loss. Finally, all these 4 losses will together in the joint loss for the de-learning network to update during training. Here's a visual demonstration for progressive dilation. We can see from this figure, we use blue, red, and green to represent different dilation rates. We can see from the de-risking performance that each progressive dilation unit can successfully utilize different dilation rate to address multi-rate scales in one image. Here is the loss function for a proposed network, including the SSIM loss, the segmentation loss, the perceptual contrast loss, and the LAM perceptual image similarity loss. You can track more tech details and explanations on our paper. This is the training detail for SAPNet. We use 1,800 synthetic reading image pairs from Ring 100 training dataset. We use Eden and PyTorch to train our model with a learning rate decay strategy. It takes approximately 20 hours to converge our model with 100 approaches. This is the evaluation dataset, including some synthetic dataset and real-world reading dataset. We show one evaluation table in this presentation, and you can find more details in our paper and our supplemental material. And we can see the proposed channel residual attention, unsupervised background segmentation, perceptual contrast loss, then perceptual image similarity loss, and the added dilation and decay strategy help us achieve state-of-the-art performances. In short, all proposed model components are essential. We also show quantitative comparison using PSNR and SIM on these three synthetic reading datasets. We show our model has best overall performances. We also compare the performance of these three real-world reading images using unique and bridge skill. This table also shows our model performance is best among all. Finally, we show quantitative comparisons on MAP, MPA, and MLU. We can see our model has the best performances in terms of MPA, MAP, and MLU. Essentially, our model is very close to the ground truth performances. We also show more user study, inference time, and parameter comparisons in our paper. These are qualitative comparisons in real-world dataset. And this is qualitative comparison on synthetic reading dataset. This is the objective detection and the reading image taken from proposed COCO 150. In this figure, we can see our model has most accurate bounding box detection and group classification. Finally, we show the semantic segmentation performance and the reading image. We can see the semantic segmentation results at Cityscape 115 from this figure. Our model apparently has the best segmentation performances and is almost on par with the ground truth. In conclusion, in this paper, we propose a segmentation-aware progressive network, or SAPNet. Our model comprises of several modules, including the progressive dilated unit, the unsupervised background segmentation, the perceptual contrast loss, and the then perceptual image similarity loss. These methods combine to help us achieve a state-of-the-art performance with a real-time processing and affordable model size, and also to preserve the maximum amount of high-level semantic details. In the future, we hope to explore more about detection-driven de-risking and de-risking at suboptimal low-light conditions. Thank you.